Hello, thanks for attending our talk today. My name is Dr. Kyle Ellis. I am the Deputy Project Manager of NASA's System-Wide Safety Project. And the talk today is going to be talking about in-time system-wide safety assurance and really a concept we're calling in-time aviation safety management systems, looking at future national airspaces across the globe and really what the digital transformation of these new air traffic paradigms will look like, specifically in the context of safety. So to begin the conversation today, we want to look at what does the future national airspace system look like. And when I say national airspace system, that's every different state across the globe has their own infrastructure for that. But really, we're looking at the types of operations that might exist in those various airspaces. So we know the traditional aviation markets that are out there today with large airliners flying around. There's also the regionals that are flying around with charter operations. We're also looking at helicopter operations and general aviation. But there's a lot of new operational domains that we're considering, especially when you start looking at remotely piloted operations, high altitude, long endurance. We're looking at space launch operations happening much more frequently on the commercial sector. We're looking at high altitude balloons flying around, providing internet services and other operations such as that. And all the way down to small UAS, right? I'm in the United States, a Part 107 operator myself. So we want to make sure that all of these different types of operations can operate in harmony and as safely and efficiently as possible. So looking at this future national airspace system, it's a very exciting opportunity looking at all the different economic benefits and societal quality of life benefits that can be brought to bear with all of these different types of operations. But we already look at the national airspace systems as they exist today as a very structured standard operating procedure type of airspace. And when we look at adding new types of entrants into this airspace, it poses a problem, right? So we look at this in terms of safety assurance, right? The Safe Future Global Airspace System has to integrate these new operational domains into their airspace. And we do know that the public has generally a low tolerance for risk in aviation. We expect a certain level of safety when we look at these. And the current operations that we have in the national airspaces are very labor intensive, and they have limited ability to scale up as they're currently structured, specifically for these new entrants. And so what we're looking at now is possible solutions, and how do we collaboratively define specific concepts of operations from a vision level for advanced and scalable safety management systems that are really using this tailored service-oriented architecture that helps us better focus our safety investments that are really focused on individual operational domains that still connect into the larger system, and offering new technological solutions that help us assure safety to overcome these various barriers of this future envisioned national airspace system. And so what we're really looking to do is to achieve some form of consensus on the desirable system traits of a system that we're calling an in-time aviation safety management system, and apply that concept to relevant use cases to show how we can integrate this federated architecture, leverage all the data that's generated, and be able to look at it in the lens of safety to make sure that we can achieve the level of safety that the public will seem tolerant of moving forward to bring in these new operations. What we'd like to be able to do is leverage data and to mine that data, also look at it in much more real time as possible to identify anomalies, precursors, and trends to more proactively manage operational risks. And so what I'd like to do is really look at where we've been, where we are, and where we're going when we look at the evolution of airspace operations and safety. If you look at the initial operations, a lot of what we did with operations in the national airspace was looking very procedural, right? We could estimate and have an idea of where the planned aircraft positions would be, but really there wasn't a lot of communication back and forth depending on, when very early days looking at this. Developing new technologies like radar allowed us to know the current and estimate planned aircraft positions, which allowed us really to have a little bit tighter density in the airspace so that we could actually track and start to manage that traffic with air traffic controllers and centers all across the nation, right? If we look at all these things. And so it allowed us to have some form of separation assurance when we were looking at this. And now as we progress forward, right, if we look at where we are today, it's Epic 3, right? We're able to know and exchange current aircraft positions, which allows us to improve the efficiency of operations, improve our proactive planning for these to start to schedule operations. And that's really what we enjoy today, is really high efficiency in these. We're still able to maintain safety while boosting efficiency. And the safety management systems we have for large aircraft and airline operations allows us to start to begin to automate some of the safety monitoring alerting services, right? We can leverage that digital data that we have. Here in the United States, we actually have a service called FOQA, which is our operations data that we have, and it captures over 200 different data feeds that we can actually start to look in and see what's happening in the operations. And I know entities like IATA has the FDX system that actually allows us to look at that for all global airlines if they participate in that. Now, what we're seeing is those examples are really early representations of the digital transformation of the air traffic management system. And that really sets the stage for what we call collaborative and connected operations. And so as we move up these S-curves for technology adoption, which you see in green there, that really allows us to leverage the digital nature of the services and the operations. So it allows us to start tailoring our missions and the different types of services that are making them possible. And allows us to start to, from a safety perspective, integrate and start to be able to predict risks in the operations and mitigate them before they start to represent in the actual operations themselves. And this all sets the stage to safely incorporate higher levels of automation and autonomy, which that is what's really needed to achieve scalability for these new future envisioned operations that we talked about in the future vision of the NAS, that really represent a complex set of scalable and dynamically adaptive operations in the NAS. Right. And when we see that, to achieve the level of safety that the public expects from these types of operations, that we really need a safety management system that helps us to automatically assure this adaptive in-time safety threat management. Right. So we need to be able to do safety threat management in a way that's much more rapid than it is today. So let's go and take a look at the airspace as it is today. Right. If we look at traditional air traffic control, a lot of it relies on comms, right? We have a lot of radio activity back and forth between aircraft and ground controllers, and we have a lot of scheduling between operators and the air navigation service providers when we look at all of this. And so it's a very efficient system because there's a lot of standard operating procedures to manage the chaos that can happen from all this, right? We don't have this in terms of driving cars back and forth, and that's why the rate of accidents is much higher, right? And so we have very standardized procedures for this because it's constrained by the types of communications we have for it, right? But now as we begin to look at new concepts like the U-Space in Europe or UTM, UAS traffic management in the United States and other areas, right? It's leveraging this concept we call collaborative air traffic management. It's exchanging data in real time as we move back and forth. It's less reliant on communications, voice communications, back and forth. And so leveraging the speed of, I'll say, the internet of the air traffic management, right? That allows us to actually leverage and create these space for these new operations to fly much more collaboratively and to be able to handle a much more dynamic type of operations in the national airspace system. Now, we look at the risks of those types of operations, right? So let's just use the operational domain of an urban air taxi, for example, right? Or package delivery back and forth. So if we look at this, there's a new set of hazards, like new complexities, risks, and constraints that we don't necessarily factor in today with the operations we have, at least to the level of detail that will be needed to enable these types of operations, right? So for particular operations, if you have, say, a disposable vehicle that's carrying, dispensable cargo, right? Now you really have to consider third-party risk, right? What's the safety concern in terms of flight over people and moving vehicles, right? If you are carrying passengers, how do you handle contingency management like passenger emergencies, right? Where you might have to rapidly change your destination from the nearest airport to the nearest hospital. How do you identify and manage non-cooperative aircraft? How do you have the database to know where obstacles are, especially if you're flying under 400 feet air-to-ground altitude? How do you have logical systems that maintain monitoring of vehicle system health parameters and use that data to inform contingency management decisions? How do you know where RF interference, radio frequency interference, is going to play a factor? What happens when you lose GPS and your position, navigation, and timing solution? So these are all different complexities, risks, and constraints that we have to develop new services and ways to manage these hazards and mitigate the risks. So if we look at achieving aviation safety today, ICAO really sets the guidelines for a lot of this out of their Annex 19 for safety management systems, and it resides on 4 pillars, right? There's safety policy, risk management, safety assurance, and safety promotion. That's what makes up the 4 pillars of the safety management system. And underneath each of those, right, are specific processes. And what we're really going to focus on in the discussion today is risk management and safety assurance. Not to say that the other 2 of safety policy and safety promotion aren't as important. There's a lot of importance across all 4 of these, but in terms of technology integration, right, we look at a lot of the safety management processes, especially in terms of an operation, right, of collecting the data, analyzing that data, identifying new hazards, adjusting your risk management controls, prioritizing your resources to be able to buy down that risk or to mitigate those hazards as you identify them, and really to achieve specific safety performance goals that you set for your operation. Or if there's a regulatory, perspective on this, right, to meet those specific goals. But the problem with this is when we look at this, sometimes collecting all that data is very cumbersome and it's very labor intensive. And because there's a lot of people involved in subjectivity to analyzing all of this data, to put in a really effective, rigorous safety management system requires that human element to be able to interpret this. Right. And to think about this at the scale of operations we're talking about as we move up those epics into this highly digital infocentric NAS, as the FAA and the United States calls it, it has very limited ability to scale if we have that much human involvement for this. And so also, because it's so much data to manage, sometimes it's not fast enough to mitigate the hazards before they manifest as an actual safety incident or accident. And so that poses a problem. So this is where the concept of in-time system-wide safety assurance, or ISSA as we call it, because NASA likes its acronyms, is really looking to proactively mitigate risks and demonstrate new solutions, and we'll call those technologies and new processes that allow us to ensure safety to the community on the ground and in the air, right? And what this really does is it is 3 high-level functions of monitoring large disparate types of data, fusing that data together in a way that allows us to apply new assessment techniques to determine whether or not there's an elevated risk state, and if there is, execute some type of mitigating action, right? Whether that's an alert for some executive authority like a person to do something, or if that's triggering an automated mitigation solution. And both of those represent a safety assurance action, right? They are doing something that's actually going to prevent that accident from happening in the future. And at NASA in particular, we are approaching this iteratively and systematically and developing new technologies that demonstrate, monitor, assess, and mitigate in specific use cases. And we're doing this with a strategic implementation plan across 3 major milestones, right? The first is looking at domain-specific safety monitoring and alerting tools, and then integrating predictive technologies with domain-level applications, right? So we're developing capabilities. Now we're starting to integrate them in an overall system. And then that sets the stage, if you're following those epic curves that we showed earlier, right, to develop an adaptive in-time safety threat management system. Right, that is the in-time aviation safety management system. So we took this concept and we had our National Academies of Sciences, Engineering, and Medicine take a look at this, and they said, yes, this is exactly what we need to be doing. And they came back with a recommendation, and NASA cannot claim this acronym, but the in-time aviation safety management system. They said safety management systems as they are today, like we pointed out earlier, are very labor intensive, don't have that ability to scale. As they said, so let's work on developing 4 fundamental system element areas. And first is, let's come up with a concept of operations and prioritize the types of risk we'd like to mitigate, looking at system monitoring technologies, system analytics technologies, and coming up with unique mitigation and implementations of these, right? And that's really based off the specific operation. So that's what we're doing. So really what they're recommending is, how do you morph the safety management system into something that allows you to do this much more rapidly? And what that really means is, how do we take risk management and safety assurance and start to merge those 2 processes even more tightly together? Because they are very well connected, but a lot of people are involved in that. So we really need to start to merge those so that we can fuse the different technologies together to allow us to identify hazards through that data collection and analysis process set. And what that actually looks like is developing a set of services, functions, and capabilities, right? SFCs for short, and we call those technologies, right, that allow us to monitor large sets of data, again, assess all of that data once it's fused together, and identify new hazards, and then mitigate them before they manifest as an actual accident. And at a higher level, right, if we look at this, that really allows us to rapidly manage known operational risks, so things that we know are hazards out there, but we're just watching out for. Also identify unknown risks, right? We'll call that predictive safety. So we can start to simulate and see what new changes in the national airspace could look like with new types of entrants, and identify and start to mitigate those before we start flying them. And then also inform improved system design. So as we design new technologies, we need to assure that they perform as intended reliably, but we also need to be able to make sure and monitor over the life cycle of that system that it actually is doing what it's intended to do, right? So as we collect that data, the efficacy of the system really is being able to determine how well it's performing its functions. And if it starts to degrade over time, do we need to trigger a redesign for all of that? And all of this, as we said, is leveraging that digital transformation of the national airspace system. So it all starts with data, right? You can look at these as the ingredients to your overall recipe of safety, right? And so the information classes, we have a report by Steve Young and several other colleagues that came out in 2020. You can find that in NASA's technical report server. And if you're interested in that, we can provide that to you. But there's 16 different information classes that we've identified, and there's probably several more since we've published this, that are sourced from a variety of different places, right? The air navigation service provider has a lot of those. They come from the vehicle, many different data sources from the vehicle. Supplemental data service providers can provide process data that's necessary for this. In the United States, we have the System-Wide Information Management System, and for the UTM, the Flight Information Management System. And there's also other sources, right? Like smart cities are going to be a rich source of data as we move into this, right? So providing local weather information, looking at where its general populace is and where you should or should not fly is really important to be able to inform the safety management system, especially if you're looking at real-time operations. So let's look at this in functions here. So we look at these in terms of really 5 or 6 high-level risks, categorical risks, right? One of the major risks that we look at specifically with remotely piloted operations is flight outside of approved airspace, right? We want to make sure that they're flying where we want them to fly, and if something goes rogue, we need to make sure that we have some way to stop that vehicle from flying where it's not supposed to go, because that causes chaos and accidents that we don't want to see. We're also looking at unsafe proximity to air traffic, people on the ground, terrain, or property. All those things would be bad if we broke our proximity barriers. Critical system failures. How do you handle off-nominal events with your system, either on the ground-based systems or on the vehicle systems themselves? And how do you handle loss of control of vehicle, like envelope excursions for these? So you enter into a weather condition, right, that you can't handle anymore, specifically with smaller UAS. There's also the physical and environmental related risks, right? How do you handle weather encounters? How do you collect data about threat by person, malicious or unintentional, right? I think that's all very important data to be able to collect to know areas of higher threat. And also looking at cybersecurity. Look at the cybersecurity threats that we see with the internet today, right? And if we're talking about a highly connected federated architecture for air traffic management, cybersecurity has to be at the forefront of the design of all of these different networked architectures. So that is a huge risk set that still has a lot of research and development to be done there. There's a lot we can leverage from industry that's been done on this, but it has to be through the lens of aviation and those processes there to make sure that they're still able to perform the way they need to. And there's also those in terms of predictive and prognostic capabilities that we just haven't identified yet, right? So if we're looking at this, there's new risks that, as we develop this system that we will have to think about. So let's look at some of the different reference capabilities we've already developed. Safeguard is a NASA technology that is a constraint monitor to provide that geofencing capability. It's an independent service. We have prox threat services. We look at non-participant casualty risk assessments to help build a safety case for particular flight paths. We have a variety of different services that fit all those different those different risk categories that I just talked about. What I'd like to do is just dive into one example, right? Let's look at the non-participant casualty risk assessment. I know when we're looking at proposed operations here, they're all waiver-based primarily in the United States anyway. And one of the primary concerns, especially if we're looking at package delivery, for example, using remotely piloted UAS, the FAA, our Civil Aviation Authority, wants to know what's the risk to people on the ground, right? Because if your operation is defined, if something goes wrong, you can ditch it somewhere. we want to know what's the risk of actually hurting somebody on the ground. Third-party risk becomes a primary look. So what we're actually looking at with this capability is collecting aero model data, population density data, assessing that against a flight plan, looking at aircraft state, looking at how the weather affects that vehicle if it were to crash, and we simulate a crash every 10 meters. And we actually see what is the actual probability of causing a fatality every step of the way across your proposed flight plan. And so you can actually aggregate that risk and see what your risk posture is to third party, right, as you're looking at this. And so it's a really useful tool to be able to do pre-flight safety mitigations to say, maybe I should fly at 7 o'clock at night as opposed to 4 o'clock because the traffic is much different. So that's just one example of a capability that needs to live inside of this network for pre-flight safety. And if you can operationalize the data and update it with more real-time data, you could even begin to assess that in real time. So say you start to have a block party that pops up in your population density, you can start to avoid those types of things with your operations. So getting back to the ISMS, it is a service-oriented architecture of safety services and capabilities. And so they reside across the vehicle, the airspace service providers, and the supplemental data service providers. So much of the ISMS is driven by supplemental data service, right? Whether that's weather services or population density models or terrain models, for example. That all helps feed data to these different capabilities that reside at the entities and the actors of your architecture for your national airspace system. And so when we look at this, we're talking about safety assurance services, functions, and capabilities that help us monitor, assess, and mitigate. And it's the interconnectivity of all of these to be able to look at the aggregate safety of your operation that makes up an ISMS. So as you can imagine, every single type of operation you have, if you're an operator, will have its own version of an in-time aviation safety management system. At the system-wide level, right, you would even have an ISMS that's ingesting data that's processed from all of those operators to look at it, NAS-wide. So let's look at this in an architecture really quick, right? In the United States, so I admit that this is really tailored for some of the acronyms that we have. So if these don't resonate with you, I apologize, but really, look at the far left. It's the NAS Information Exchange, right? That's for in the United States, the System-Wide Information Management System or the Flight Information Management System. And that's our bridge to our Civil Aviation Authority for managing the system-wide data. Underneath of that, you have the ANSPs, right? The air traffic control, the UAS service supplier, or the provider of services for UAM for a particular, I like to refer to it as a local air navigation service provider. That's Kyle's term. Then there's fleet management, right, which is the operator themselves, and then there's the vehicles themselves, right? So you see how this tiers down, and I actually went in and took a box, and you see that in gray there, where it's at least 3 tiers of networks, right? You have a network where all the different ANSPs are connecting into the swimmer FIMS feed. You at least have one where the operators, and there's a multitude of operators that connect with the local ANSP, and then there's the operator has a fleet of vehicles that they have to connect with, right? So there's the operator digital network, the ATM digital network, and the common NAS digital network. Now, across that, there's the operational systems just to pull off the operations as envisioned, right? That's the traffic management systems. That's the requisite data that needs to transport back and forth to negotiate air traffic management and to manage your fleet of vehicles. What we're showing here is the in-time aviation safety management system is the other side of that, right? It is a connected part of that overall system that's doing the flight data management to capture all of the safety related data from those operational systems and begin to monitor that data, make assessments on that data, and inform mitigation strategies on off-nominal events and anomalies. So looking at this, there's also the supplemental data service providers that are also helping monitor, assess, and mitigate and providing requisite data to enable those safety services to be effective, and also the operational systems to be effective. I should include that as well. So I did this just really quickly. This is Kyle's take. There are a variety of services, functions, and capabilities. This list will look different depending on the specific use case you have. I'm going to go into how we kind of define what that looks like here in a minute. So looking at the in-time aviation safety management system is important, when you're defining what that architecture looks like to apply an operational context to it, right? So part of our roadmap with the system-wide safety project, for which I'm helping manage, right, is to outline what some reference architectures could look like that would be needed to assure safety of increasingly complex operations. So we're actually looking at 4 specific use cases right now within our project. We're looking at wildfire fighting, operating within a temporary flight restriction out in California. We're looking at search and rescue and post-hurricane disaster relief on the East Coast. We're looking at medical courier delivery in a variety of different locations that are trying to operate in urban and suburban environments. And we're talking about critical medicines flying from one location to another. We're looking at, even scaling up to organ deliveries, right? If you can help avoid traffic for some of that. So those are examples of that. And then we're also looking at even more complex type of operations in unevacuated urban area disasters, right? So that's where you still have people on the ground that you'd be flying over. You don't know what type of infrastructure exists in terms of comm links, and we need operations that are resilient to operate within those types of environments. And so as I describe all of those, let's move over to the chart on the right. What's interesting when you look at defining these is they all have a unique set of criteria that defines their risk criticality, their complexity and uncertainty, right? When you're flying in specific environments, right, the complexity of your operation really defines the number of certain capabilities and services you need to be able to assure safety of that. And if you're flying in uncertain environments, like we talked about the unevacuated urban disaster area, right, where you don't know if you have good GPS or a good radio connect or comm connection to your remotely piloted operations, for example, that's an uncertain situation that you need services to help mitigate. If you're flying over people, right, or if you're flying in some high critical payload, right, that adjusts your risk criticality, right? So as that slides to the right, you need to assure that all those capabilities that are using to address the complexity and uncertainty of your operation are assured to a level that provides the reliability needed to prove that you have a sound safety case for those operations. Right, and I do want to mention that all these really do build up towards high density urban air taxi operations, which to us is the hardest type of operation to deploy, specifically if it's highly autonomous without a pilot on board. And so that is where you would be flying in high urban centers where there's people and third party risk, plus you have high critical payloads. So that risk criticality is pegged all the way to the right. You're flying in urban centers with many, many services interconnected. So the complexity and the uncertainty of the environment is relatively high. Right. And so really what we're looking to do is mature the specific capabilities that would build up this architecture and demonstrate them in these types of use cases. So I kind of went through this already. So when we're defining these, right, there's really at least these 4 criteria, right? And there's many more, right? When you look at this, of looking at how is your defining your use case, right? You're defining your mission is how is your vehicle flown, right? Whether it's closed loop pilot doing all the pitch, attitude, roll, thrust yourself, or are you remotely piloting it where it's got a little bit more, fly-by-wire capability? Do you have visual observers? Is it beyond visual line of sight? Is it autonomous, right? That adds to the complexity of the services you needed. Also looking at what type of environment you have. Is it a known or predictable environment, all the way to unknown and predictable and unpredictable, right? So it's all these different characteristics of things that you need to consider when flying in various environments. The airspace will have different constraints and restrictions depending on what you want to do, and also consideration for what other type of aircraft that may not be as equipped as you flying in your shared airspace, right? So defining that is incredibly important, and what type of air navigation surveillance provider that you'll be dealing with, right? Is it UTM? Is it ATM? Is it monitored, unmonitored by radar? All of those really feed into defining your contingency management. Is it all managed by a person? Is there some level of automation in there? Is it fully autonomous? And all that goes into defining the hazards for your safety case and the needs for defining what your safety case and safety arguments are. So let's talk about that next. So when we're talking about establishing this safety framework, you have a very specific use case for your concept of operations. You then need to perform a hazard analysis to identify what the different hazards and safety critical risks are. And then working with your civil aviation authority, typically you would have to go through and determine what does acceptable safety assurance look like, right? And so you can go through a process like SORA, for example, to see what the risk matrix looks like for your different risks. And then you can start to define what types of capabilities and services you would need in an ISMS to build that safety case and to assure safety of the operations. Then we're collecting data and building that architecture. We're flying that, and this is part of the NASA process we're doing right now, is now developing the ISMS in a reference mission and basically demonstrating that with those mission operations. And that allows us to generate lots and lots of data. And what we're trying to do is generate even more data that allows us then to inform what would standards look like? What are the minimum data exchange requirements of a system like this to assure this type of standard scenario, right? And so that's really what we're looking at here. So it's a reference architecture for an ISMS that can help inform standards. And that's really what we're working on today, and we'll be working on here in the near future. Because eventually what we'd like to do is to have this new construct of a federated architecture in-time aviation safety management system be a new safety framework that has set requirements that would allow us to move from a waiver-based approach to a more standards-based approach for different operations. And part of our iterative development process is doing this spiral development. So those top blocks that are kind of covered up by this one represents how we will cycle through this numerous times, and working with industry partners such as yourselves might be an opportunity for us to work together on some of these things to build out what this framework looks like. Going a little bit further down the rabbit hole, right, when we're defining these capabilities, like I said, it's very important to define your concept of operations and what your specific use case is, and define which vehicle you're using, right? So small UAS with certain envelope and performance characteristics. We do that hazard assessment. We do that hazard severity and likelihood to determine what the risk matrix looks like. And then you can start to develop, I need services that mitigate these risks, and this is what they look like. So we gave an example set on the right, of different types of capabilities. Now, what's important to look at here is, depending on your concept of operations and the roles of responsibilities of the different actors or agents in your operation, defines how much, we call it maturity level, but how much automation and autonomy is in each of those capabilities, right? And then crossing that with the risk matrix based off hazard severity and likelihood, and going through a risk assessment like SORA allows you to determine what level of assurance, right? How much reliability needs to be built into each one of those various levels of automation capabilities that you have, right? And so you can see here on our chart on the right, we have a variety. And the point is, not all of them are matured or have the same level of automation or autonomy. It's just based off of your use case and the roles and responsibilities of the operation. So to wrap all of this up, when we look at this, I'm going to bring it back to this picture here. The in-time system-wide safety assurance approach and the in-time aviation safety management system that is representative of that safety framework allows us to really look at pre-flight safety, in-flight safety, and post-flight safety. And it's a little bit of a paradigm shift because we're actually moving from what's traditionally been a post-flight safety assessment into much more, that's why we call it in time, much more near real-time operations. Not that we don't do the post-flight safety, we're just adding to it, right? And so we're really developing all these different types of capabilities to help us mitigate these new types of risks and hazards with these new entrant operations. And with that, I'm going to hand it over to my colleague, Andrew Carter, to give a real-world example of how industry is building out technologies representative of some of these new concepts we talked about just now.
Awesome. Thank you, Kyle. Let me pop this up. Let me know when that guy is visible to you.
Looks good.
Perfect. Awesome. So appreciate Kyle giving us the walkthrough of kind of the history behind in-time system-wide safety assurance. And I'll jump into a little more on the industry side. So appreciate you having me today. My name is Andrew Carter, and I'm the CTO of Resilience. And really, it's always great to hear groups like NASA and the FAA that we work with on how they're thinking of in-time system-wide safety assurance. Resilience has actually been working with NASA for the last 3 years to implement and commercialize many of the concepts that Kyle just talked about. So I'm going to give you a high-level overview of Resilience and how we're thinking of ISSA, or in-time system-wide safety assurance, from an industry perspective. Then I'll also discuss some of the real-world deployments and applications for in-time system-wide safety assurance in UAS ecosystems that we're working in around the world. So as an overview, throughout the evolution of mobility, we've always traditionally relied on a human operator to provide really the safety and resilience layer, acting as a sensor within a vehicle and really as a last resort when something goes wrong. But as we're looking forward to these future of advanced mobilities and the rapid rise of connected technologies, we're creating a challenge. In these dynamic cyber-physical ecosystems, the various computers and systems will rely on each other, as well as disparate data streams to make decisions. If these ecosystems are not reliable and resilient, we're never going to get to the trillion-dollar advanced mobility markets that we've all been promised, and frankly, that we're all excited for. These interconnected cyber-physical systems are relying on data from each other to make decisions, and computers can only make decisions based on the information they have. If they have bad information, they're going to start making bad decisions. Without a human in the loop providing the resiliency, a software solution is needed to prevent catastrophic results. 3 years ago, we saw this need forming within the UAS industry to increase the system resilience and for these evolving autonomous ecosystems. Our prior experience working with NASA told us that, or working with the FAA told us that they would never allow complex drone operations if the tenets of safety assurance that Kyle just spoke about were not addressed. And last summer, the FAA really validated this belief, working alongside NASA by issuing the memorandum describing requirements necessary for achieving complex drone operations. And we have been simultaneously working with Kyle's team at NASA and the FAA to help shape these requirements to achieve safety assurance covered by this memo. I want to take a minute and dive into that FAA memo because the FAA has taken a slightly different take on type certifying UAS than many other areas of the world. Oops. And apparently I have a transition. And so really what the FAA has said is that any drones that are anything that's on the drone itself, that's flying on the drone, is part of a type certification process. But if the component is not flying on the drone, it falls into this bucket called associated elements. And this includes everything, including ground control stations and communications links, which were previously, and in many parts of the world, contributing to a part of that UAS or that unmanned aircraft system. Associated elements also include other infrastructure such as sensors and services needed to increase the operational area and complexity of operations and scale the UAS ecosystem. Common UAS aviation risks that are traditionally handled by air traffic controllers and airport infrastructure around communications, navigation, surveillance, weather, and traffic management are also placed into this associated elements bin. But the FAA says that just because the components are not going through type certification, they don't just get a free pass. There still needs to be an approval process. And although the exact process is still being worked out, in their associated elements memo, the FAA lays out many considerations that will need to be followed. And many of those considerations, to no real surprise, mirror the concepts being pushed through NASA from this in-time system-wide safety assurance concept. In particular, the FAA calls out the need for in-service monitoring criteria to detect out-of-compliance performance and initiate corrective action, which is essentially a concise FAA jargony way of saying many of the things Kyle and I have been discussing. So we're currently working with partners such as Cal Analytics to go through this process within a DAA system to help the FAA understand how do you approve associated elements. Resilience has developed our in-time system-wide safety assurance platform called Framework, which stands for Fault Recovery and Isolation Health Monitoring Framework. Framework is a highly configurable software suite that's built on the tenets of ISSA. And when we look at that, we're literally looking at those three pillars that Kyle mentioned of monitoring, assessment, and mitigation. With monitoring, we monitor the health, integrity, and performance of all the various components and services that are involved in this UAS ecosystem. For things around communications, navigation, surveillance, weather sensors, web-based software services such as traffic management or detect and avoid. And our goal there is really to detect any kind of adverse or off-nominal conditions that are occurring. Once we detect something's wrong, then we get to that assessment stage. And really, when we talk about assessment on the industry side, we're really looking at impact assessment. So we're trying to understand what operations or operators are affected. If it's a sensor issue, is there a geographic region that's being affected? Or maybe some software service is down for maintenance or an upgrade. And so there's a timeline of a couple hours where you're not going to have some capability. And finally, our goal there is to provide those mitigations. A lot of that right now looks like human in the loop, but eventually we want to get to a fully automated system. And so we look at, how do we maximize system uptime and availability? And how do we minimize disruption to the ecosystem? These mitigations may look like constraints so that operators can start to reroute around areas that are unsafe, or we may cut off bad data sources so we don't propagate that bad data to the machine learning algorithms that are actually trying to make decisions based on the data they have. Our software is adaptable to different environments using our runtime configurable rules engine and a web-based microservice architecture. And a key tenet in what we do is that we understand that we are never going to get an inside look into all the systems that we're playing with. So we treat every component as a black box and don't rely on specific hardware or any kind of proprietary data sets. Now, most people familiar with the Advanced Air Mobility or UAS ecosystem or UTM ecosystem, first question we usually get is, where do these ISSA capabilities fit into the tech stack? It's kind of easy to overlay them as a concept, But as you start to actually develop the technology, you need to figure out which pieces you plug into and work with. So this image is a simplistic view of the tech stack. And at the bottom row incorporates much of the smart infrastructure and associated elements, which are vital to reducing the risk for UAS operations. Traffic management services such as USSs, PSUs, USSPs, pick your acronym for what part of the world you're in, generally have some relationship with the operators and are using data and services from infrastructure to enable safe operations. And on the right, we show Part 135 operators or drone delivery operators, which usually have an ops and control center and are really controlling the whole tech stack and trying to put it all together. We generally sit between the enabling infrastructure and the operators, or the USSs, monitoring the system components and providing insights and alerts when any kind of adverse or off-nominal conditions occur. In the spirit of in-time system-wide safety assurance, our goal is to work with ecosystem players to mitigate the issues in the safest possible manner to really enable this in-time incident prevention. Rather than, as Kyle talked about, with the historically the safety management systems, which have the big feedback loop where you do the incident analysis, there's a lot of people involved, and it can actually be years before either policy or procedure or requirements or something changes to actually prevent that next issue. We're really trying to do this in time to prevent the current issue that's happening or that's emerging. So now I'll get into some examples of what we're seeing in the real world. While many of these examples are a little forward-leaning, we're actually working in environments that incorporate all of these right now. So here's an example of how Framework plays into a smart city environment. This slide shows infrastructure nodes that we are working with our friends at the Autonomy Institute in Austin, Texas, that serve as technology warehouses, and some of the capabilities that live inside them. These nodes are actively being deployed down in the Austin area, like I mentioned. What happens when a car crashes into one of these smart nodes and you lose part of the network? Our goal with Framework is to detect an event like this that's affected this node, and then try to assess the remaining functionality. We can determine the health and the performance of the affected sensors and orchestrate automated mitigations that can adjust coverage volumes to account for sensor degradations. One possible mitigation is that we can issue a no-fly zone or US volume restriction or some kind of constraint into the airspace to facilitate rerouting of drone operations. Our goal is to, with events like this that would be potentially catastrophic and could bring down an entire network, we really want them to only register as a blip to the ecosystem as we work behind the scenes to keep these systems up and running through the messy real-world issues which we all know will occur. Vertiports are an area that we're particularly excited about as they move from concrete slabs to this highly automated sensor-rich environment. We've just begun integration with multiple vertiport companies as they develop the vertiport tech stack to include surveillance comms, navigation aids, weather sensors, battery charging, and all of the associated digital infrastructure such as flow control and airspace management. Framework's monitoring this system of systems and playing a role when issues arise. One of the key elements to monitor is system performance. Most systems are not binary, on or off. For instance, radar systems may degrade in certain weather conditions, or comm systems may experience interference. These degradations need to be able to be detected and their impacts assessed. What is the impact to operation flow if you can turn, and in turn, how does that impact air traffic management? Framework provides insights to operators and airspace managers about these anticipated impacts. Another example of a service we are working on as a part of a NASA-funded effort with Kyle's team is our Weather Data Sensor Monitoring Service, or WISDOM. Low-altitude wind in urban environments is a pretty big unknown right now, and obviously critically important to drone operations. Sensors to measure wind come in many shapes and sizes, and a dense deployment of aviation-grade sensors would be extremely cost-prohibitive. So we looked at how can we gather the data that we need in a more cost-effective manner. Our friends at our micro weather friends at True Weather Solutions have a computational fluid dynamic model for winds around 3D structures. We're able to actually use that model to determine if the cheap, lower cost wind sensors are actually operating correctly and putting out good data into the ecosystem, or maybe they're degraded or faulted. And this enables us to put orders of magnitude cheaper wind sensors scattered throughout an urban environment to inform and drive real-time and predicted wind data. Currently, these sensors are being deployed in the Hampton, Virginia area in the US, and we're testing out their services. Another area that we're excited about is our work down in Australia. Resilience is currently working with our partners at OneSky on the Air Services Australia Flight Information Management System, or FIMS. One of the exciting capabilities we're able to showcase to them was our ability to do real-time data quality assurance on various ecosystem data feeds. Shown here is our data quality assurance capability integrated with the FIMS and USS systems. When a human's watching the screen and a track starts to bounce around or act erratic or, do something funny, a human immediately is suspicious of the accuracy of that data they're seeing. Currently in UTM, things have largely been focused on making sure the UAS stays inside of some kind of operational area through conformance monitoring. The issue that we've seen there is that a UAS track can bounce all over the volume and that can actually jump outside of that volume for quite a while, as long as it makes it back into that volume every once in a while. As you can see from this image, just because the track is in the volume doesn't necessarily give you confidence that the track is where it is. There could be many issues going on, such as navigation issues, could be high latency, could be some processing or tracking issues. And so to solve this problem, we're looking at the telemetry data on a track-by-track basis and can determine when things look, quote unquote, funny, and provide alerts back to the system for someone to take a closer look. As you can imagine, as things scale and operations increase, airspace managers and operators will not be able to monitor everything all at once, and will be increasingly reliant on these types of alerts, as well as automated contingency management decision aids to safely manage the airspace in their operations. Thank you for listening today. It's always exciting to share what we've been working on to a broader audience. And my contact information is at the bottom of this page. Feel free to reach out if you have any questions.